Hi, welcome back to my channel, and for today's video, we will be talking about the index of a subgroup in a group. And thank you so much for your all undying support. And if you are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. And if you have a request of topic you'd like me to discuss, then just comment down there in the comment section of this video. Okay, so let's start now. So we have a definition here that provided you have a subgroup of a given group G. So in this case, our subgroup H is a subgroup of a group G. The index of H in G, denoted by the symbol, is the cardinal number of the set of distinct right, respectively distinct left, cosets of H and G. And we will use this notation here. So if you're still wondering about the distinct right and left cosets of H and G, you might want to check on this thumbnail here for the video explanation about the cosets. So how do we intuitively understand on this definition? So assuming that this is our group G, although it doesn't look like that way because just for the purpose of illustration, you would understand how does it look like. Although it doesn't look like that way in the sense of being a group. But suppose, for example, this is our group here, and then this is our actually a subgroup H here. So if you would like to consider, say for example, the left coset. So let's say we pick an element A from G. So we pick A here from this group G, and then we multiply that. So either it could be on the left or it could be in the right. So let's focus on the left cosets, for instance. So what happened here, it would actually generate another set in which it contains, in this case, an A here as a product of elements from H. And so if we go again with another generation, then we may pick another set here, and so on. So if we are going to count that, that's technically the index of subgroup in a group G. So that's the point there. And just so you know that when we pick a coset here in this group G, always remember that a coset may or may not be a subgroup of a group G. It's technically just a set. So by that, we will consider a remark here from the given definition. Number one, this index of H in G does not depend. So it does not whether the right or left cosets are used. So right or left cosets are used. Number two remark out from this definition is that suppose, for example, your subgroup is actually the subgroup generated by the identity, then we may write this way. HA is equal to, so this is the right coset, so we have HA such that H is an element of this one. And so I can write this in this form. That's EA. And since the product of any element to the identity, that's the same as A. So this is this will work for every A in G. So meaning to say that if we take the index of the subgroup generated by the identity in G, then that's technically the cardinality of G, because again, we're actually counting all the elements of G in the sense that this is an identity. That's it. So by this, we will introduce a theorem here. So the theorem says that if you have three groups, the K, H, and G, and you have this condition such that the K is a subgroup of H and the H is a subgroup of G, then we have this equality. So it's basically like a tower here. So if you have a G here, you have H here, you have K here. So basically, the index of K in G is the same as if we multiply the index of H in G and the index of K in H. So basically, you're just combining these two here and you get this. So how do we prove that? Observe that we discussed on the previous video, so you might want to check on thumbnail here, that your G is basically the union of this one, the right cosets. Okay? So, with your AI in G, and so the cardinality of I, which is basically the number of indices, is basically the index of H in G. And the cosets, HAI, are mutually disjoint. So when we say it's mutually disjoint, meaning to say that if we have this HAI equals HAJ, that simply means I and J equals J. So that's it. So that means we consider this one. And also the same similar argument is that H equals the union of K BJ with BJ in H, and then the number of indices is actually the index of K in H, and the cosets K, B, J are mutually disjoint. So that's the same argument we have presented on this here. So what does it mean? So if I'm gonna write this again, like the first equation we made here, so I have G equals the union of H, I in I. So I can write this as the union of the union of K, B, J. It's AI, this is J in J, and this is I in I. So I hope you don't confuse with this. I am just substituting this here to this here for H. Okay? And so since I got that, I can write this as the union of K, B, J, A, I, where this is I, J, element of I cross J. So that means it's a Cartesian product of these indices here. By this, it suffices to show that this coset here is also mutually disjoint. Like the cosets are mutually disjoint. So by that we have we will jump into conclusion that this will be something like that. But in order for us to show first that this is mutually disjoint, let's consider this first. If KBJ AI and that's equal to KBR80, so that implies you have BJAI times BR80 inverse, and that's element of K. So this is by the definition of our presentation on the last video. And so, what does it mean? Since this is an element of K, I can equate this into an element in K. So that's for some K in K. So it means to say that I can multiply the inverse of this to the right. So that means I have BJAI, and so this is equal to K BR80. So what's the implication here? Observe that your BJ and your AI and your K here are elements of H. Why? Because, of course, this is for the reason that K is an element of H, because our assumption says that K is a subgroup of H, and so this follows that K is a subset of H, meaning to say that all these elements from K are also elements in H. So since that's an element of H, we must have the fact that this is implying that your AI H is equal to H80. So what's the implication of this? This implies that your I here is equal to T, this one, and your BJ is equal to KBR. Okay, so what's the implication? Meaning that your KBJ is actually KKBR. So meaning I'm just multiplying these both sides by K. And so KKBR is just the same as KBR because that's inclusion as being element of groups. So this implies that J equals R. So remember that cosets, um, cosets K, B, J, A, I are mutually, so this is capital K, sorry, disjoint. So that's it. So by that, since we have shown that these are mutually disjoint, then I can now use the fact that the index of GK is actually the same as the cardinality of I cross J because it's already shown that they are mutually disjoint. So this is the same as the cardinality of I times the cardinality of J. And what's the cardinality of I? This is actually the index of H in G rather. And this J here is the index of K in H. So therefore, we have proven the claim of the theorem. That's it. So if you have any questions or clarification, you can comment down there so that I would know and we can discuss that. So this is just a short video introduction for the index of a subgroup in a group. So for the next video, we will also discuss some consequence of this specific topic. Like we will introduce the Lagrange theorem, the normal subgroups, and so on. So thank you guys for watching. If you have questions, again, don't forget to comment down there so that I would know. Or if you have any thing you would like to me to discuss, then just comment down there. Thank you and have a great day. Bye for now.